Okay, so we're going to do a little work here with springs and spring constant and harmonic motion and waves. And we're going to begin by just taking a measurement here of where the weight is on the mirrored surface. So it looks like it's about 6.5 centimeters. So go ahead and write that down. The original position was 6.5 centimeters. Then I'm going to add 50 grams of mass. So it's stamped 50, and I'm going to put that 50 gram mass on here, and we're going to get a new measurement. And our new measurement in the mirror is about 9. So I'll go with 9 centimeters. So we had a change of 6.5 centimeter to 9 centimeters. I'll go ahead and I'll set this aside for a moment. We'll do a little work on finding out how stretchy this spring is, and we'll come back to it in just a minute. So that was our stretch, which means we have a 2.5 centimeter stretch, which is 0.025 meter stretch. So when we added that mass of 50 grams, so 50 grams is actually going to give us a certain amount of force. Turn it into kilograms and then multiply by the gravity constant, and we get a weight of 0.05 times 9.8, 0.49 newtons. So with 0.49 newtons added, we end up having a stretch in the spring of 0.025 meters. And that's all we need to find the spring constant. So we take the force divided by the distance stretched, and that'll tell us K, how stretchy the spring is. So we have 0.49 divided by 0.025. And we get a spring constant of 19.6 Newton over meter. So that's the first thing, is just find out how stretchy the spring is. Then we can use that stretchiness to figure out some different things. One thing we could do is we could figure out the period then with this. So the period, the time it takes for an oscillation, is going to be equal to 2 pi times the square root of m over k. So we can put in our k value of 19.6. We can put in the mass. Now, have to be kind of careful here. We want to put in the entire mass, not just the mass of the hanging thing. So if we look here, you can see that we have 50 grams plus 50 grams, or 100 grams for our mass. So that'd be 0.1 kgs multiplied by 2 pi, and that should tell me the time for one oscillation. So we have 2 pi times square root of 0.1 divided by 19.6, which was the k value. So it should take about 0.448 seconds to go through an oscillation. 0.448. So we'll do it for 10t. If that's t, what does 10t equal? Should give us 4.48 seconds to do 10 oscillations. We'll see if this holds true and see if this really works. It doesn't really matter what the amplitude is when we do this. We just want to kind of back here a bit. We just want to pull it down a little bit and see what happens. So you can see it in the mirror right there where it's starting at. I'll try to give it an amplitude of about 1 centimeter, give or take a couple. Try to get a little bit of vantage point here. So it's sitting about 9.5, just like we saw last time. I'm going to pull it down a centimeter, and I'm going to let it go, but then I'm also going to time it here. So I got a stopwatch. You can see that it's zeroed. I'm going to go ahead and pull this down a centimeter. down to about 10 and a half. I'm going to release it. I'm going to try to count 10 periods, and then I'll stop it. It goes pretty quick. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that it worked pretty well. I mean, it wasn't perfect, but I did end up with 4.78. And my prediction was 4.48. So it's definitely within the possibility of the certainty of the experiment, meaning I expected it to have a little bit of error. So when we actually did it, it worked pretty well, which lets me know that my K value was probably correct. Now, what would this wave look like is another question entirely. So we'll create a y and x axis here. I started by pulling it down 1 centimeter, and then it would go up 1 centimeter past the x axis and back down 1 centimeter, so 2 centimeters total on the way up. And we just kind of label these points like that, and then our period was 0.448 is what we calculated, so I'll go with that. And so half a period, 0.224 would be right there. And then we want to add 0.224 to 0.448, and we get 0.672. And then add another 0.224, 0.896. All we got to do is connect these dots to get our wave-like patterns. We get this sine or cosine curve that kind of moves up and down. Now, some of the key points in this wave are the amplitude, which we said was 0.01 meter. We also have the top, which is called the crest, and the bottom, which is called the trough. We can also call these both antinodes. We have the distance from crest to crest, which is the wavelength, which I don't really know because I have nothing to compare this to see how fast it could travel, but that would be the wavelength. One last thing I could do is figure out how fast the spring was moving when it got to the middle. So as it's moving up and down, you know, it reaches this equilibrium point at some point. It's going up and down and up and down. And it's right here in the middle. We want to know what that speed is, the velocity of the object. So we can figure out what that is by using this relationship. We know kinetic energy is 1/2 mv squared. We just studied that. For a spring, its potential energy is 1/2 ka squared. I can get rid of the halves. I'm left with v squared is equal to ka squared if I divide by the mass. And if I square root both sides, I'm left with the radical ka squared over m. I can just put my numbers in here and I can solve for the velocity. So remember, this particular spring had a stretchiness of 19.6. I pulled it down a centimeter. The mass was 100 grams. I can figure out how many meters per second it has when it crosses that midpoint. So we go 19.6 times 0.01 squared divided by 0.1 and then square root the whole thing. And you get 0.14 for its maximum velocity, which isn't really that fast, but it's not really traveling a great distance in a short period of time. So that's pretty much how you find and do everything with the spring. Alright, thanks. See ya.